All right, so a complete graph is a graph that has an edge between each pair of vertices. Now, if you look at the graph below, we can see it's not complete because we don't have an edge between A and D, and we also don't have an edge between B and C. Otherwise, we have everything else has an edge that's connecting it, but those two we don't have edges to. So, that's kind of the key here. We don't have that edge and that edge. Therefore, because of that, it's not a complete graph. Okay. So complete graphs are significant because every complete graph with three or more vertices has a Hamilton circuit. Now the graph, again, has no Hamilton circuits because it's not a complete graph. Now this graph below has an edge between each pair, so now we've added those in, and so because of that, the graph is complete and it has a Hamilton circuit. Actually has a complete repertoire of Hamilton circuits. For example, one could be we go from here down on this one, we go from A to B and B to C and C to D and D back up to A. So that would be one. Now, any two circuits that pass through the same vertices in the same order will be considered to be the same. For example, there are four different sequences of letters that produce the same Hamilton circuit on the graph. We can do A, B, C, D, A. We can do B, C, D, A, B, or we can do C, D, A, B, C, or we can do D, A, B, C, D. Basically, we're starting here and we end up here, or we start here and we go around and we end up here, or we start here and we go around and we end up back there, or we start here and we work our way around. And each one of those basically is the same thing. Okay. So uh, the difference is just where it's starting at. So those are all considered the same. All right. So what we do to avoid this is what we have to do is start always assuming beginning with A. So we're going to start always with the same vertex. In this case, we're going to start with A, and then we're going to try to figure out how many ways to do that. And so then we're going to work our way around A, B, C, D, A. So that is our first one up here that we see, and that's what we've done. Now the next one we could do is we could, well, let's instead of going from B to C, well, A, B, D, C back up to A, and that would give us that one. And so now we've gone all the different ways from B. So now let's go starting with C. So we could go A, C, B, D, A, or we could go A, C, D, B, A, and that would get us the next two. And then we have to think, okay, well, now we've done B's and C's, so now let's go A, D, and then we can either go B, C, A or A, D, C, B, A. And so that would get us the next two. And each of those are different because they're going in different orders. They're not the same thing. And so that's going to be how we're going to avoid getting duplicates is we're always going to start with the same vertex, and then we're going to move from there to different ones. Okay. So now the number of Hamilton circuits in a complete graph. Well, the number of those is going to be depending on how many vertices there are. So if we have n vertices, then what we do is we're going to find n minus 1 factorial. And we haven't talked about that yet, but the exclamation mark here represents factorial. So if we have n factorial, that means we're going to take n times n minus 1 times n minus 2 times n minus 3 times n minus 4 and so on until we take times 2 times 1. Okay, and we'll multiply all those together, and that will give us n factorial. So, for instance, 4 factorial means it's going to be 4. Subtract 1 from that, 3. Subtract 1 from that, 2. Subtract 1 from that would be 1. Multiply all those together, and we're going to end up with 24. Okay. So if we want to determine the number of Hamilton circuits in a complete graph with three vertices, well, we're just going to take 3 minus 1 factorial. Well, 3 minus 1 is going to be 2, so that's going to be 2 factorial. Well, that's going to be 2 times 1, which is 2. All right, so what if we have 6 vertices? Well, that's going to be 6 minus 1 factorial, and that's going to be 5 factorial, which is going to be 5 times 4 times 3 times 2 times 1. And if we plug that into our calculator, we're going to have 5 times 4 is 20, and that's going to be times 6, so that's going to give us 120. Now, this one will give us 10 minus 1 factorial, which is just 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And if we put all that into our calculator, we'll get a bigger number. And I'm not going to do that in my head, but that's going to be 362,880. Now, once we get to the section in our class that deals with factorials more, we'll show you how to do that on your calculator, and that'll help you a lot more. But until then, you can really just multiply it out like this and just take 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and we can get that. All right. So let's stop there and we'll come back with weighted graphs.